Assalamualaikum and good day to Dr. Nordin and everyone. My name is Siti Aisyah Binti Mohd Isham, matrix number 207026. Today I will be presenting about statics. Did you know what is statics? Statics is the study that deals with the equilibrium of bodies that either at rest or move with a constant velocity. So in this presentation, I will divide it into 4 parts. First part, we will discuss about basic concept in statics. Secondly, we will discuss about force systems, which include 2D and 3D. Next, we will discuss about equilibrium, which includes equilibrium of a particle and equilibrium of a rigid body. Lastly, we will also talk about analysis of friction in bodies and structures under static condition. Now let's move on to basic concept in statics. There are 4 basic quantities used in statics, which are length, time, mass, and force. Moreover, we also need to know about idealizations. Idealizations is a model that are used in mechanics in order to simplify application of the theory. So here we will consider 3 important idealizations. First is particle. A particle has a mass but size can be neglected. Next is rigid body. A rigid body is a combination of large number of particles which does not deform when force is applied. Lastly is concentrated force. Concentrated force is the effect of a loading that acts at a point on a body. Furthermore, Newton's third law of motion is also a basic concept that we need to learn in statics. This law stated that an object is at rest or moving with a constant velocity. So the summation of force is equal to 0. Second law stated that an object experiences acceleration when subjected to net force, F equal to ma. Third law stated that for every action, there is an equal and opposite reaction. Now let us move to force system. Physical quantities in statics are measured using either scalar or vector. Scalar is a quantity that has magnitude only, for example, length, mass, and time. Vector is a quantity that has magnitude and direction, for example, force and moment. Next, we move to vector addition of forces, 2 dimensions. First and foremost, we will see how to solve addition of 2 forces by using parallelogram law and trigonometry. Next, we will see how to solve addition of coplanar forces system by using either scalar notation or Cartesian vector notation. So for 2D force system, first we will see the addition of 2 forces by using parallelogram law. So first and foremost, we need to find where the resultant force line is. As you can see in the figure here, there are 2 component forces, F1 and F2, acting on this pin. So these forces can be added together to form the resultant force, Fr equals F1 plus F2. So how can we actually construct this resultant force line here? First, from head of F2, draw a line that is parallel to F1, and then from head of F1, draw a line that is parallel to F2. So the diagonal of this parallelogram forms the resultant force. After we're done with the sketch, next we use the triangle rule. As you can see, the half portion of this parallelogram is actually a triangle. From this triangle, we can determine the magnitude of resultant force by using law of cosines and its direction by using law of sinus. Now let's see the example of addition of 2 forces by using parallelogram law. Determine the magnitude of the component force F and the magnitude of the resultant force Fr if Fr is directed along the positive y-axis. First and foremost, we need to draw the parallel line. For this F here, the parallel line is from head of 200 pound and then draw a line that is parallel to F1. And then the parallel line for this 200 pound is from head of F and draw a line that is parallel to 200 pound. So from this parallelogram, the half portion is actually a triangle. So we can use the law of sinus to find the resultant force and force F, because the angles are already given. So F over sine 60 equals to 200 over sine 45, and F is equal to 245 pound. And then Fr over sine 75 equals to 200 over sine 45. So FR is equal to 273 found. Next, for 2D, we see the addition of coplanar forces system, where the force is resolved into two components along the X and Y axis. We can represent these components in two ways using either scalar notation or Cartesian vector notation. So for scalar notation, first we resolve all the coplanar forces in Fx and Fy component, and then we sum all the Fx and Fy, and then we find the magnitude of resultant force. By using this formula, we determine the direction of the resultant force by using this formula. While for the Cartesian vector notation, we represent the Fx and Fy component in terms of Cartesian unit vector I and j. First, we add up all the coplanar forces according to I and j components, and then the resultant force is equals to F1 plus F2 and F3. So let's see the example of addition of coplanar forces system. The link is subjected to two forces, F1 and F2. Determine the magnitude and direction of the resultant force. So let's see how to solve this problem by using scalar notation first. For scalar notation, first we need to resolve the F1 and F2 force in terms of Fx and Fy components. Summation of Fx for F1 in x-axis is 600 cos 30, and for F2 in the x-axis is negative 400 sine 45. And then we find the magnitude of the resultant force by using this formula. So we already find the magnitude of resultant force. Next, we find the direction of resultant force by using this formula. As for Cartesian vector notation, we need to represent the Fx and Fy component in terms of Cartesian unit vector I and j. For F1 is equal to 600 cos 30i plus 600 sine 30j. For F2 is equals to negative 400 sine 45i plus 400 cos 45j. And then we find the resultant force. Fr is equals to F1 plus F2, and we find the magnitude of resultant force by using the same formula, direction of the resultant force, also by using the same formula. So final answer, the magnitude of resultant force is equals to 629 Newton, and the direction is 67.9 degree. So far we have discussed about the vector addition of two forces in two dimensions. So we have discussed about the addition of two forces by using parallelogram law and trigonometry, and also we already see the addition of coplanar forces system by using either scalar notation or Cartesian vector notation. Next, we see the addition of Cartesian vector. So in 3D, we will see three situations. Situation 1 is coordinate direction angles, and situation 2 is about not coordinate direction angles, and situation 3 is about position vector. So in 3D, it is easier for us to express the vector in Cartesian vector form. Cartesian vector I, j, and k components along the x, y, and z axis. So for 3D, we will look at situation 1 first, which is coordinate direction angles. Basically, when we are given the problem that has coordinate direction angles, alpha, beta, and gamma, then we will use this situation to solve the problem. In this situation 1, it is important to note that coordinate direction angle alpha, beta, and gamma is measured from the positive x, y, and z axis to the tail. For example, alpha is measured from x positive axis to the tail, beta is measured from positive y axis to the tail, and gamma is measured from positive z axis to the tail. So this is the formula of direction cosines. When the coordinate direction angles alpha, beta, and gamma are given, we can use this formula to find fx, fy, and fz. Then we can write the force in Cartesian vector form. And then to find the magnitude of Cartesian vector, we can use this formula. There is also an important relation among the direction cosines. You can use this formula when you are only given two of the coordinate angles. For example, you are given alpha and beta. So you can find gamma by using this relation. Next, for 3D, in situation 2 is non-coordinate direction angles, means that, for example, angles of 60 and 45 here, defining the direction of F, are not coordinate direction angles. In this case, the application of parallelogram law and trigonometry are needed to resolve F into its X, Y, and Z component. So Fz here equals to F sine theta, and F prime is here. F prime equals to F cos theta, and then Fx is here equals to F prime cos theta, and Fy is here equals to F prime sine theta. So when we already find the Fx, Fy, and Fz by using this formula, then we can find the magnitude of Cartesian vector by using this formula. So let's see the example of 3D problems. Express the force F as a Cartesian vector and determine the coordinate direction angles of F. So in this figure here, this is situation 2, which is, this is not coordinate direction angles. In situation 2, we need to resolve F into X, Y, and Z components. Fz is here. Fz is equals to 100 sine 60, and F prime is here. F prime is equal to 100 cos 60, and then Fx is here. Fx equals to F prime cos 45, and then Fy is here, is equals to F prime sine 45 degree. So we already find the Fz, Fx, and Fy. Then we can express the force as Cartesian vector here. So next, we need to find the coordinate direction angles. Coordinate direction angles is in situation 1. So by using this formula, okay, we need to find alpha, beta, and gamma. Fx, Fy, and Fz, we already calculated it just now. And F here is equals to 100. And then by using this formula, alpha, we get 69.3. Beta, we get 111 degree. And gamma, we get 30 degree. So if you want to sketch it on the X, Y, and Z axis, so alpha is from positive X axis to the tail. Beta is from positive Y axis to the tail. Gamma is from positive Z axis to the tail. Next, the last case for 3D is position vector, which is in situation 3. So we use this situation when we are given the Cartesian force vector directed between 2 points in space. So first we establish a position vector from A to B. So basically A to B is coordinate B minus coordinate A. And then we find the magnitude of AB, which represents the length. And then we formulating the unit vector in the direction of AB, which is lambda AB is equal to AB over magnitude of AB. Lastly, we express this force as Cartesian vector since F has a magnitude and direction specified by lambda AB, then the FAB is equals to F times with the lambda AB. Now let's see the example of 3D situation 3, which is position vector. The roof is supported by cables. If the cables exerted forces FAB equals 100 Newton and FAC equals 120 Newton on the wall hooked at A, determine the resultant force acting at A. Express the result as a Cartesian vector. So first, for AB, we establish position vector from A to B. So for AB is coordinate B minus coordinate A, so 4I minus 4K. And then we find the magnitude of AB, which equals to 5.66 meter. And then we formulating the unit vector in the direction of AB, which is the lambda AB. Lambda AB is here. AB divided by magnitude of AB. Lastly, we express the force as Cartesian vector. So FAB times with the lambda AB. FAB is 100 here. Therefore, FAB is equals to 70.7 I minus 70.7 K. Next, we establish a position vector from A to C. So coordinate C minus coordinate A. So it is 4I plus 2J minus 4K. And then we find the magnitude of AC is equals to 6 meter. And then we formulating the unit vector in the direction of AC, which is the lambda AC. Lambda AC equals to AC divided by magnitude AC. This is lambda AC. So lastly, we express the force as Cartesian vector. So FAC times with the lambda AC. So the FAC in Cartesian vector is 80I plus 40J minus 80K. For the resultant force, we simply add the force FAB plus FAC, 70.7I plus 80I, and then for J is 40J, and then for K is negative 70.7 minus 80K. So this is the resultant force expressed as Cartesian vector. So far, we have discussed about 3D force systems, which has three situations: situation 1, situation 2, and situation 3. Now we move on to the third part, which is equilibrium. Equilibrium means the particle is at rest or moving at constant velocity, which is summation of F is equals to 0, equilibrium of a particle. In coplanar force system 2D, Fx equals to 0, Fy equals to 0. In 3D force system, Fx, Fy, and Fz is equals to 0. So the first step in solving any equilibrium problem is to draw the free body diagram. Next is equilibrium of a rigid body. The sum of the forces acting on the body is equals to 0. So for 2D equilibrium, Fx equal to 0, Fy equals to 0. So this equation states that the sum of the moments of all the forces in the system about point O is equals to 0. So in 3D equilibrium, also Fx, Fy, Fz equals to 0, and the moment also equals to 0. As usual, the first step in solving any equilibrium problem is to draw the free body diagram. Now let's see the example equilibrium of a particle in 2D system. So determine the tension in cables BA and BC necessary to support the 60 kg cylinder. So first and foremost, in equilibrium question, first thing we need to do is to draw the free body diagram. B in the middle here, and then we have tension A and tension C, and below is the tension BD, which is the weight of the cylinder, 60 kg. We convert it into Newton. For equilibrium, summation of Fx is equal to 0 and summation of Fy is equal to 0. We need to resolve the tension into Fx and Fy component. Tc in X component is Tc cos 45, and for Ta is negative 4 over 5 Ta equal to 0. For Y component, Tc here, Tc sine 45, and for Ta is 3 over 5 Ta, and for Bd is negative 60 times 9.81 Newton equals to 0. Solve this first, and we put the Ta in the front. So we substitute this Ta here, and then we can get the Tc, which is equals to 476 Newton. And then we substitute Tc here, and then we get Ta equals to 420 Newton. Next, we see the example of equilibrium of a rigid body. So this is 2D equilibrium. The box wrench is used to tighten the bolt at A, okay, at point A. If the wrench does not turn when the load is applied to the handle, determine the torque or moment applied to the bolt and the force of the wrench on the bolt. First, we need to draw the free body diagram. Here is point A, here is point B, and here is point C. And then this is in millimeter, we convert it into meter. In equilibrium 2D, summation of fx equals to 0, summation of fy equals to 0. So first we resolve the force at x component. At point A, ax. At point B, x over there. So negative 52, 5 over 13. And then x here is over here, 30 cos 60 equals 0. And then we can find the ax. Next, we resolve the force into y component. Y is here, upward here. And then at point B, the y is below here. So negative 52, 12 over 13. And then y here at point C, negative 30 sine 60 equals to 0. And then we can find ay is equals to 74 Newton. So we can find the force of wrench on the bolt, which is at point A, by using this formula. So we can get the Fa is equals to 74.1 Newton. And then we need to determine the torque or moment applied to the bolt, which is at point A. So for moment, we use this formula, M equals to Fd. Moment at point A is MA, which is counterclockwise, so it is positive. The force at point B that is perpendicular to the point A is downward here. So negative 52, 12 over 13 times with D here is 0.3 meter. And then at point C, the force that is perpendicular to point A is here. This is the force. So negative 30 sine 60 times with the D, which is 0.3 plus 0.4. And then equals to 0. Then we can find the moment at point A, which is 32.6 Newton meter. So the last part of my presentation is analysis of friction in bodies and structures under static condition. We focus on dry friction. Friction is a tangential force that resists the movement of one surface relative to another. There are two types of friction, static friction and kinetic friction. If no sliding occurs, the maximum value for the friction force is equal to the product of the coefficient of static friction and the normal force at the surface. In this case, the motion between contacting surfaces is impending. If sliding occurs at a slow speed, then the friction force is the product of the coefficient of kinetic friction and the normal force at the surface. Next is wedges. Wedges are inclined planes used to adjust the elevation of structural or mechanical parts. For example, the wedge shown here, which is used to lift the block by applying a force to the wedge. So this is the free body diagram of the block, free body diagram of the wedge. And the two force equilibrium equations are used to relate the forces acting on the wedge. Next is screws. Square threaded screws are used to move heavy loads. They represent an inclined plane wrapped around a cylinder. Next is flat belts. Flat belts are often used to transmit the torque developed by a motor to a wheel attached to a pump, fan, or blower. The force needed to move a flat belt over a rough curved surface depends only on the angle of belt contact, beta, and the coefficient of friction. This is the free body diagram of belt segment in contact with the surface. As shown here, the normal and frictional forces acting at different points along the belt will vary both in magnitude and direction. Due to this unknown distribution, the analysis of the problem will first require a study of the forces acting on a differential element of the belt. Finally, this is the equation used related to frictional forces acting on a flat belt. Next is coil bearings, and this Collar bearings are used in machines to support an axial load on a rotating shaft. The frictional analysis of collar bearings and this requires looking at a differential element of the contact area. The normal force is determined from force equilibrium along the shaft, and the moment needed to turn the shaft at a constant rate is determined from the moment equilibrium about the shaft's axis. So finally, this is the equation used related to bearing surfaces that is subjected to constant pressure. Next, we look at frictional forces of journal bearings. When a shaft or axle is subjected to lateral loads, a journal bearing is commonly used for supports. So this is a typical journal bearing support. As the shaft rotates, the contact point moves up the wall of the bearing to some point A where slipping occurs. If the vertical load acting at the end of the shaft is P, then the bearing reactive force R acting at A will be equal and opposite to P. The moment needed to maintain constant rotation of the shaft can be found by summing moments about the z-axis of the shaft. And lastly, this is the equation used related to the journal bearings. Lastly, rolling resistance. The resistance of a wheel to rolling over a surface is caused by localized deformation of the two materials in contact. This causes the resultant normal force acting on the rolling body to be inclined so that it provides a component that acts in the opposite direction of the applied force P, causing the motion. This effect is characterized using the coefficient of rolling resistance, A, which is determined from the experiment. And lastly, this is the equation related to rolling resistance. So I have come to the end of my presentation. Thank you so much, and I hope you will get a bit benefit from this presentation. Thank you.